Okay, so currently we are learning about the hazard problem. So there are three types of hazard. One is structure hazard. And second is data hazard that we will learn today. And last one is control hazard. Okay, what's the structure hazard? So due to the resource conflict, right? So resource is not enough. The hazard is happening. So to solve the structure hazard, the easiest way is we are putting more hardware resource, right? So for instance, the memory is conflicted and we are preparing the separate memory. Okay. So let's look at the data hazard. So data hazard is occurred when there is a data dependency. Okay, so let's think about the two instructions, which is add and subtraction. Add and subtraction. Okay, so if we are not applying the pipelining, then what is happening? Let's look at it. Okay, so here, the first add instruction is adding two register value, T0 and T1, and then result is stored into the S0 register, right? And then after add is completed, then subtraction instruction is reading S0 register and T3 register, and then that result is stored into the T2 register. Okay, so if there is no pipelining, it's okay. There is no problem, right? After we are completing the add instruction, and then subtraction is starting. But let's think about the pipelining. So it's like this. Okay, so there is some dependency. So let's draw the pipelining. So add instruction is starting, instruction fetch, and then instruction decode is reading register value, and execution is computing the addition and memory operation. But here in this case, memory stage is not doing anything. In the write back, the rest value is updated. Okay. And subtraction is just starting here, instruction fetch. And then subtraction is trying to read register in instruction decode stage. But you can see that when the $1 is updated by instruction add, at which stage the $1's register value is updated? In the write back, right? So write back is actually updating the $1 register. Okay. So until $1 is updated, whenever we are reading the register 1, then it is old data. It's a stale data. Okay. So here we can't read it because $1 is not updated. Here we can't, right? And here, so it's totally depending on when we are updating the $1 and when we are reading the data. Okay. So here, let's assume that ID is reading register. It doesn't take so much time. Let's think about it. Just take the half clock. Okay, so it's reading at this moment, and write back, which is writing the data register, is writing in the first half clock. Okay, so when the clock is falling, then the register value is updated, and when the clock is rising, then the register value is red. Okay, so at this moment, the value is written, and here ID, the clock is rising, then the register value is fetched. Okay, so here in this case, when we can start the subtraction. Subtraction read can start here, right? because write back is already completed in the add instruction. So we can start instruction decode at this moment, which means that how many bubbles do we have to insert? How many cycles do we have to wait for the subtraction? So we cannot, there is no half cycle, right? Everything is integer cycle. So how many bubbles do we have to add? So we have insert one bubble, another bubble. Okay, and next here, we are assuming that the instruction decode is reading data at this moment. So we don't need bubble, right? Because write back is already updating the data at the falling edge. Okay, so if the write back is completed when the rising edge, then maybe we need 3 bubbles, 3 cycles. But here, what we are assuming is that write back is a little bit occurred earlier. Okay, so write back is happening half cycle earlier, and reading is happening at the end of clock cycle. Okay. So what we are assuming is that write is already completed before we are reading the register. So how many bubbles? There are 2 bubbles. Yeah, 2 bubbles. Okay. So which means that because of this data dependence, we have to wait 2 cycles. Okay. So it looks like this, right? So if it is pipelining without bubble, then the instruction decode should be occurred here. But because of these 2 bubbles, the ID instruction decode is delayed by 2 cycles. Okay, so we have to pay 2 cycle overhead, right? So because of this data hazard, we have to pay 2 cycles. So it's 2 cycles. Okay. So then, how can we remove or reduce these bubbles? We have to solve this data hazard, right? Because this data hazard will be occurred frequently due to the dependency. So in many cases, we are sequentially computing some values so that this data hazard is happening a lot. So how can you reduce this bubble? So let's look at the add instruction and this subtraction. Okay, again. Okay, so we know that the raised value is updated when the write back stage, right? So the raised value is updated at write back stage. So write back stage is actually at the last stage, right? This last stage. But when the addition result is available, when addition value is available, at which pipeline stage? Yeah, after execution, then we know the result, right? But the result is not written to the register yet. But anyway, we know the result, right? So if we are making some special hardware, which means that we are modifying the hardware to consider this data hazard. So what if add instruction is executed here and instruction decode and execution, but we know that at the last stage here, the data is available, right? So $1's value is available, even $1's value is not updated yet. Okay, so we know that this is $2 plus $3 value. Okay, And next instruction, subtraction. That is starting here. A second. And it's trying to read, right? But the read is not available because that value is available at the end of instruction decode. So here in this case, how many bubble? We need one bubble, right? So then this value can be used as an instruction decode. However, we can remove this bubble also. Why? When do we need $1 bubble? At which stage? In the subtraction? In the subtraction, yeah. Before we are starting the execution, if the $1's value is available, then we can use it, right? So before we are execution, so subtraction is executed here. Before we are executing, the value is available, right? This value is just directly provided to the next instruction. So even though this instruction decode in the subtraction, this is reading old data, right? This is reading old data. But if the execution stage can read the recently computed value instead of using the raised value, then we don't need any bubble. Right? So what hardware do we need? We need hardware to provide the execution result is just provided to the input of the execution stage in the next instruction. So this mechanism is called forwarding. Forwarding. Or is the same bypassing. Okay, so we are implementing some special additional hardware, which is forwarding the previous result from the ALU execution to the ALU input for the next instruction directly. So that special part is called forwarding logic. Okay. So if we are implementing this forwarding logic, then we can avoid the data hazard. Okay, so we have no bubble at all for this data hazard, right? So this forwarding mechanism can solve the data hazard problem. Okay, so using this hardware, so it's the hardware solution. Okay, so using the hardware, we can solve the data hazard problem. So structure hazard case also, we are putting more hardware, right? So if we can solve the problem using the hardware, then that problem is not gonna be hard to solve, okay? So this can be easily solvable using this forwarding, okay? So forwarding, we already mentioned. So from the previous execution result is provided to the input of the next instruction for execution stage. Okay, so using the forwarding, maybe we can solve the data hazard, but still there is a data hazard. Okay. So we'll use load use data hazard. So in the previous example, there are two R-type instructions, right? R-type or maybe some arithmetic operations. Suppose arithmetic operation. But let's think about some memory operation, like load instruction. Load, the low one. And then this is doing addition using the fetch the data. Okay. So there is a data dependency. So the difference is that in the previous case, the previous instruction is arithmetic operation or logical operation, right? So now it is memory operation. Okay. So then It's different. Load instruction is instruction fetch, instruction decode, execution, data memory access, and write back. So we will use forwarding, okay, for this case also. But when the $1's value is available, at which stage? In the ALE operation case, at the end of the execution stage, the data is available, right? The value is available. But load instruction case, yeah, definitely at the end of memory. Here we know that, okay? So we know the data from the memory, okay? Even though this is not updated to the register yet. So this is load and this is add instruction. Add instruction is starting here. And it is trying to decode. But we know that the execution should be receiving the data, right? Before it's starting. Can you start here? No, because the red part, which is available data, is not available when execution stage is starting. So this cannot be starting here. So we can start execution at this moment. Okay, and then right. Okay, so how many bubbles do we need? Yeah, we need a single bubble. So even we are using forwarding logic because it's forwarding, right? So memory is provided to the input of execution directly, but still we need one bubble. Okay, so load use data hazard case, we cannot avoid the bubble using hardware. Okay, so using hardware we can't. Using hardware means forwarding logic. Forwarding, maybe we can reduce. We can reduce the bubble. To 1. Right? So single bubble, because of this forwarding logic, we can reduce the single bubble. If we don't have the forwarding logic, then maybe we have to pay like 3 bubbles. Okay. But anyway, then how can we reduce this bubble? As I mentioned, we cannot solve that bubble using hardware, right? So hardware-wise, we can't. Then there is another way, right? We have hardware and also we have software, right? So we have to use software approach. Okay. So this figure is showing the load use data hazard part. Okay. So software approach. Software approach means actually this is compiler approach. Compiler is doing. Okay. So what compiler is doing is a compiler is reading some high-level language like a C code, and then is generating the low-level language, assembly and machine code, right? So software means the compiler is actually placing the each instruction. So it compiler generating like a load instruction, add. So for instance, it's $1, $0, $2, and this is using $1, $3, $4, and there is another instruction load, $5. And then there is another one, add. This is using $5. So let's think about this case. Here, how many bubbles do we need? So there is load use bubble, and there is another bubble. So we have to pay 2 bubbles. By exchanging the instruction, can we reduce the bubble? Let's think about to change the location of these 2 instructions. Is it possible to change? Yeah, because the add instruction and the next load instruction are independent, right? They're independent. So we can change the order. So here load. And here we are executing add. And add. Okay, so in this case, how many bubbles? So here there's dependency between this one to here, right? But there is some instruction, right? If this instruction is not available, then we have to wait. We cannot execute it, so we have to pay bubble. But here, this can be executable, so we don't need to pay any bubble between this first and third instruction. And second, from between second to the fourth, we don't need to pay bubble, so 0 bubble. Okay. So if we change the order of execution, we can minimize or reduce the bubbles caused by data hazard. So this one is called scheduling or rescheduling. So scheduling means that we are determining the order, right? Order of the code. So if we are changing the order of the code, then we can reduce this bubble. Okay. So that is actually the main job of compiler. So if compiler can change in the order of the code, then it can improve the performance by reducing the number of bubbles. Okay. So, to do that, compiler has to analyze there is a dependency between these 2 instructions, and is possible then is moving the instruction to some place. And if there are many candidates, then maybe it has to choose the best place. Okay. Okay, so this is called scheduling to avoid bubble. So reorder code to avoid the use of load. Okay, so load use data hazard. So here there are 2 instructions, A equal B plus E and C equal B plus F. If we are generating the instruction, then so B, load B and load E, and it is generating the A. And it is storing the A. And next one is loading F, computing C, and storing the C. Okay, so these 2 instructions. But we know that this instruction, load instruction, can move earlier. So it can be moved anyway, any place. So if we are moving this one to the earlier, then there is no bubble, right? So there is no dependency. Okay, so we can reduce 2 bubbles. So here, the first one case, it has 2 bubbles, so it's 13 cycles because of 2 bubble. And second one has 0 bubble, so we can save 2 cycles. So which means that we can improve the performance by 20% almost. So that's a lot. Okay, so for this data result, we have two approaches. One is hardware approach. Data result. Hardware is folding logic. And still, but we can find load case data dependency. So in that case, we are using the software approach, which is compiling, which is called scheduling. Okay. So in most cases, hardware software approach means that it is compiler approach. So compiler is changing the order of the instruction, then we can improve the performance. Okay. So we are completing the two hazards, structure hazard and data hazard. So structure hazard case, using hardware, we can solve the problem. So it's easiest, right? And data hazard case, some part of the problem can be solved by hardware, and still there is some minor, not minor, but there is some issues. In the case, we can reduce the bubble using the code scheduling. But maybe in some case, we can't reduce the bubbles because there are no rooms to move. In that case, we have to pay bubble for the data hazard. Okay, so last one is control hazard. So control hazard is the most difficult part to solve. So control hazard, control means it is related to the pro and counter. So it's a jumping or branching, okay? So control hazard means it is related to the branch instruction. Okay, so branch instruction is really hard to implement. So let's look at what is happening. Okay, so here. So we have some instruction. Then here there is a branch instruction. So branch instruction is comparing two register value and jumping some place. And then there is a following instruction, and there is some place. Okay, so let's look at this case. For the pipelining, instruction decode and execution and memory and write back. The second one, branch equal instruction is starting here, instruction fetch, instruction decode, and execution, memory, and write back. When the result, whether we are jumping or not, so at which stage we know that? At which stage we know that whether this branch is branching or is not branching? Yeah, EX stage. So when this ending of the EX stage, so at this moment, we know whether it is subtraction instruction or it is end instruction, right? If it's different, then subtraction should be executed. If it's different, it is equal, then we have to execute end instruction. Okay. So after this execution stage, then we can start instruction fetch. So then how many bubbles do we need? Okay, so we need a bubble here. So we need two bubbles. It's a lot, right? So anyway, we have to reduce this bubble. So then, so first, the east way is that we are putting more hardware, right? Like a folding logic. So which means that, is it possible? So the first way is hardware. Maybe we cannot eliminate these bubbles, but maybe we can reduce the number of bubbles, right? So here there is two bubbles. Is it possible to reduce one bubble? Yeah, we can. So how? In the current implementation, so the branch equal instruction is comparing the two raised value, right? Whether this is equal or it's not equal, right? That is actually the output of ALU, right? But comparing the two values equal or different is easy or is difficult. So whether it's equal or different, we just need to execute XOR operation, right? XOR means just whether it's equal or not equal. It's much easier, it doesn't take so much time compared with like addition operation. Okay, it's very short. It doesn't take so much time. So what you can do is, instead of computing the comparison at the execution stage, we can do it in the instruction decode stage. Okay, so in the instruction decode stage, original one case, it is reading the value from the register, right? So instruction decode, what it's doing is providing the source register, second source, then it is generating the two register value, right? And actually in the register, it's comparing in the execution stage. But instead of that, there we are making some special, not special, we are just comparing these two values, okay, before the ALU stage. Okay, so the clock is changing, then the value is available here, then at the same time the value is coming out one short time. So we know that the output of this value at instruction decode stage. Okay, so the next instruction can be starting at the end of instruction decode, because the comparison is completed in the instruction decode stage. Okay, so then the number of bubbles is reduced to 1. Okay, actually that's the reason why we have branch equal instruction and branch not equal instruction only, because branch like less than, this means that it has to do subtraction, right? Compare whether this is small or this is large. Comparing like a subtraction takes much more time than just equality check. So this subtraction cannot be completed in the instruction decode stage. That's the reason why branch something is not available. Only the simplest comparison is only available, like equal or not equal. That can be completed in the instruction decode stage. Okay, so now control header is reduced to the 1. Okay, so one bubble we need. So we determine branch output. So branch output, whether it's taken, so jumping, or not taken, it's not jumping at ID stage. Okay, so we are reducing the 1 cycle earlier. Okay, but still we have one bubble. then how can we solve that problem? That's the question, right? That's the question. First, we are just using the simple way, okay? So simplistic way. We will learn about some fixed approach. So we will use some branch prediction mechanism. Branch prediction. So branch case, we don't know whether this is taken or is not taken. Taken means it's jumping, not taken means it's not jumping. Right? So branch prediction means we are just predicting the branch. Branch prediction. So simple think about the not taken approach. So not taken approach means we are just assuming that the branch will not be branching. Okay. So there is instruction something, and there is a branch. It's comparing and it's doing the label, and there is some instruction, and then here there is some label. There is another instruction. Okay. Then what we are assuming is this branch instruction is not jumping. Okay, so not taken approach case. So branch is starting here, instruction fetch, decode, execution. Before that, there is an instruction fetch, decode, execution, write back. Okay, so in the previous case, after instruction decode stage, we know that whether this is the branching or not, right? Here, we are just assuming that it's not taken. Then which instruction should be fetched? Yeah, subtraction. It's just assuming that the next instruction is just executed. So the result is available here at the end of the instruction decode, but regardless of that result, it is just fetching the instruction in the next location. So subtraction is just fetched. And then its instruction decode is executed here. But before it is starting this stage, we know that whether this is correct or not. Because at this moment, the branch equal result, we know that, right? Whether this is equal or not. So if the prediction is correct, then we are just executing the subtraction. Okay, just keep going because it's correct. If it's incorrect, then so prediction is incorrect. Then what we have to do? Incorrect, then which instruction should be executed? And should be executed. What about the subtraction? We should not execute it, right? It's incorrect. So if it's incorrect, then we are not executing the subtraction. It's nullified. Okay. So then the number of bubble is what? It depending on. If we are assuming that it's not taken, right? But actually when we are learning the program, so we are learning the program 100 times, okay? 100 times, but not taken is happening 20 times, and taken happening 80 times. Then what is bubble? How many bubble? We have to pay bubble only taken is happening. If the branch is taken, then the subtraction is invalid, right? So it's turning to the bubble. So we have to pay bubble, right? So what is the probability that our prediction is correct? Correct. Is among 100 case, only 20% is correct because we are not taken. How many cases is incorrect? It is 80% is incorrect. So correct case, how many bubble do we have to pay? 0 bubble. Incorrect case, we have to pay 1 bubble, right? So if our prediction is incorrect, then we have to pay 1 bubble. So then what's the average bubble? Average, on average, 0, 0.2, 1 by 0.8, so 0.8 bubble. Okay, so bubble is 0.8. Okay, so bubble is reduced to less than 1, but still it's not 0. Okay, it's totally depending on the behavior of the program. So program is the prediction, the branch is not taken, is happening a lot, then our prediction guarantees better performance. Otherwise, it's not going to be improved so much. Okay, so this is not taken. Then there is another one, taken, right? Taken case, it is assuming that branch is always jumping. Okay, so add branch equal subtraction and label, and then what is happening is in patch, decode, execution, and right. And branch equal is starting here insertion fetch, and at the end of stage of insertion decode, we know whether it's a branch and which instructions to be executed in the taken mode between subtraction and end. Which instruction should be fetched? End. So end is fetched. And then we know that whether this is correct or not. If it's correct, then this is just keep going. Okay. If it's incorrect, then this should be nullified. So we have to pay the bubble. So it's very easy. If the branch prediction is correct, then 0 bubble. If branch prediction is incorrect, then we have to pay 1 bubble. So there are 2 branch prediction, not taken and taken. Okay. So then how we are applying this not taken and taken? So that's the question, right? So whether we are predicting the branch is taken or is not taken. So we have to do it. So branch prediction. So for the branch prediction, there are two approaches. One is static prediction, and the other is dynamic prediction. So branch prediction, there are two branches, right? Prediction taken or not taken. Okay, so we have to static prediction case. For each branch, we are just fixed whether that is taken or is not taken. So for each branch, the prediction, whether this is taken or not taken, is fixed. Okay, so it's not changing. Dynamic prediction case, the branch taken or not taken is dynamically changing at one time. Okay. So this is dynamically changing. This is based on the history. Okay. So dynamic prediction is more complicated because it has to look at the history of whether that instruction was taken or not taken in the previous time. Okay, so by looking at some history, then it is using that history to predict the branch. So static prediction is very simple, right? We are just fixing. Okay, so which approach is good? So we have a branch here, branch something, and there is some label here, and there is another branch and something and branch here. So let's assume that the first one is branching forward for the branch. Second one is jumping to backward. Okay. Let's look at this backward. When this backward branching is happening in C code, so in C code branch, this branch instruction is generated from the if statement, right? Is there any other statement that generates in the branch? If statement and while, right? Do while, for this kind of statement can generate the branch instruction, right? Okay, so when you implement this for loop, do you remember the structure? So what is it? This for case, the last one is checking and then it is forwarding, right? It's forwarding. So then this backward is something to back. When this is happening, for, while, these are loop, right? Loop structure. So that is executed a lot. So here, this case, which is better? It is jumping back or it is jumping forward, which is happening more frequently. Loop case, that loop is just executed once or that loop is executed several times. So for instance, loop is like 100. Then how many times this branch is happening? 100 times, right? So 100 times, whether this is jumping back or is jumping forward. In most cases, it's backward. 100 times is jumping back, right? And then the last case, it is just going to next when it's exiting from the loop. So most case, when the branch is jumping back, that means it is actually representing loop. Loop case, this jumping back is happening, branch back is happening. So loop case is better to take in the branch, right? So fixed case, jumping backward, we are using take for the prediction. Because backward means that this is like a loop structure. Loop structure case, taken is much better because many times it is jumping. Forwarding case, it is happening for the if statement. So forwarding case, normally we are using the not taken approach. Okay, so if we are looking at the branch, that branch, we know the label, right? So then we know that the label part is positive, which means that it's forward. Forwarding case is using the not taken prediction. If the label part is backward, it's a negative value, then it is using the taken prediction. Then many case, it is showing the better performance. Okay, so that is static prediction. So by looking at the instruction, the precision is fixed, whether this is taken or not taken. Okay. Okay, so next time we will continue about this dynamic prediction. Okay, so dynamic prediction case, we have to keep preserving the history of the branch. Okay, so we learn about the 1-bit prediction and 2-bit prediction, and also we learn about the some special trick of the MIPS for this control header. Okay. Okay, so any question? Final exam. Actually, I don't know yet. Maybe next Monday I will announce about it. But when is the final exam week? Do you know? June 3rd or June 2nd? June 3rd. But anyway, I think after we are finishing June 3rd, okay, finishing the dynamic prediction, then we are almost completing the chapter 4. Okay, so we are only covering the control header part, so data header, the pipeline header. Then we are completing the chapter 4. Then you are just finishing the project that you are making the MIPS processor, but you don't need to implementing this pipelining in your design. Okay, you should not implementing this pipelining in your design. Okay. Then maybe we will have final exam maybe end of 2nd week or 1st of 3rd week. Okay. Okay, so yeah, I will determine in the next Monday. Bye.